Hello, welcome back to the NPTEL online certification course on deep learning. So, from our previous lecture, we have started discussion on the generative model, and a particular model that we are discussing about is what is known as variational autoencoder. So, unlike in case of discriminative models, in case of generative model, what you need is that given a latent description of the object or the image, the generator network is expected to generate an image or an impression of that particular object. So, that is what generative network does, unlike in case of discriminative network, where the input to the network is an image or an object, and the network has to classify that object into one of the known categories. So, that is the difference between a generative network and a discriminative network. So, in our previous lecture, we have given a brief introduction to the generative model, and we have said that what we have discussed previously, that is traditional autoencoder, the decoder part of the traditional autoencoder can act as a generative model, but we have discussed about what is the limitation of that autoencoder or traditional autoencoder, why it cannot be used as a generative network. Then we have also talked about the intuitions between the variational autoencoder. Today we will talk about variational inference, and we will see that practically how a variational autoencoder can be implemented. So, let us briefly recapitulate what we have done in our previous lecture. So, this diagram shows we have shown how the latent variable is generated by a traditional autoencoder and a variational autoencoder. So, given these images as shown over here, a variational autoencoder for each attribute which is learned during the training of the autoencoder, the variational autoencoder for every descriptor or every attribute tries to find out the position of the attribute in the latent space, as well as the range of that attribute or the variance of that attribute in the latent space, as shown over here. Whereas, a traditional autoencoder assigns a fixed value to different attributes. So, for example, in this particular set of figures, if you look at the first diagram, the first image, you can't say that the boy is smiling, which is not very apparent. So, a traditional autoencoder assigns a very small value, and in this case it is a negative value, to that particular attribute smile. Similarly, over here, coming to the same attribute smile, we cannot say that this is a smiling face, right. So, the traditional autoencoder will assign a value something around 0 to that particular attribute smile, whereas this is a smiling face. So, traditional autoencoder will assign a high value to this particular attribute smile. Against this, if you look at what kind of descriptors or the values the variational autoencoder is expected to give, it is not expected to give a specific value to a particular attribute, but it is expected to give the position of the mean of that value, and around that mean what is the range over which that particular attribute may vary. So, that is what is given in case of variational autoencoder as given over here. So, given this, so variational autoencoder, instead of giving a deterministic latent code which is given by traditional autoencoder, in case of variational autoencoder, we are interested to learn the distribution of the latent code. That is coming, if I say that this distribution is a Gaussian distribution or a normal distribution, we are interested to learn what is the mean of that distribution and what is the variance of that distribution. So, for example, as we have just seen that for that particular attribute smile, it is more intuitive to determine the range of smile value for a face instead of an absolute smile value as is given by a traditional autoencoder. So, in case of variational autoencoder, instead of a deterministic code, the variational autoencoder will output the mean and standard deviation of each component of the latent vector or each attribute which is learned during the training process. So, now as we said that once we have a distribution of the variables or the distribution of the latent vector, you can sample a latent vector from that distribution and pass that latent vector to the generator model or the decoder, and using that the generator can generate an image. So, that is our aim of our variational autoencoder. However, because now we are going to learn the distribution, we want that the distribution should be as compact as possible, and as we also want to interpolate between different objects to have different combinations, we also like to have the distributions as generated by different objects should be as close as possible. So, actually the kind of distribution that we would like to have is something like this, as shown here. But while training, the network may converge to a situation of this form, where the means of different categories of images or different classes of images, these means become widely different from each other. So, we not only want that the distribution of every category should be compact, we also want the distributions of different categories, they should be as close as possible. So, in order to do that, what you do is you impose a prior distribution. We say that each of the distributions of individual categories should be as close as possible to a prior distribution, and this prior distribution is usually taken as a zero mean Gaussian with variance of 1 or unit variance. And then you try to find out the KL divergence between each of the distributions of the latent vectors from each of the categories and the prior distribution that we want to impose, and this KL divergence has to be minimized. So, if we want to minimize this KL divergence, basically every distribution tries to be as close as possible to the center in your latent space, and all the distributions become very, very close. So, effectively what we get is something like this, that for while training the network, for every category we have our data loss component and we also have a KL divergence loss component. So, the data loss component or the reconstruction loss component will try to make the distribution of every category very compact, and minimization of the KL divergence component will try to encourage encodings from different inputs to be clustered about the center of the latent space. So, with this, now the network creates clusters if the network tries to create clusters for different categories in different regions in the latent space, then KL divergence loss will penalize that and will try to bring those distributions, those clusters as close as possible towards the center of the latent space. So, as a result, the kind of data distribution or the latent vector distribution that we get is something like this. If you use only reconstruction loss or only the data loss component, in that case the latent vectors coming from the images of the same category, they try to form the clusters, as shown in this particular image, as shown in this image, where you find that the data coming from different categories, they become they form clusters, but these clusters are spread in your feature space or the latent space. If I used only the KL divergence loss, what we said that the KL divergence loss, we try to minimize the KL divergence between a prior probability distribution, which is zero mean Gaussian with unit variance, and the distribution that we get from the training data. And if I do not impose any reconstruction loss, then all these distributions will try to be same as the distribution, the normal distribution with zero mean Gaussian with unit variance, and the data distribution for all the classes will be something like this. So, you find that on both the cases the generator or the decoder find it difficult to reconstruct the image. In this particular case, if I sample a data point over here, somewhere here, then as this data point was never seen by the decoder will not be able to reconstruct what is to be reconstructed out of here, out of this particular latent distribution. So, what the decoder will generate may not be meaningful. Whereas, if I have a situation like this, here you find that the latent vectors from all different categories, they are zero mean Gaussian with unit variance. So, as a result, you have lost the structural information of the data or the class identity of different data. And because you have lost the class identity or the structural information of your data, again the decoder does not know what to generate, because every latent vector coming from all different categories, they are sent to the decoder. So, here if you find that on the right hand side what we have shown is, if you apply both the KL divergence and the reconstruction loss, in that case you find that the data belonging to different categories, they have formed their own cluster. At the same time, globally all these distributions come closer and give a compact cluster of the latent vectors. And this is the one which is ideally suited for the reconstruction purpose, because now my latent basis or the distribution of the feature vectors is very compact. So, if I take any point or sample any point from any of the distributions and pass it to the decoder or the generator will be able to generate an image out of that particular sampled latent vector. So, this is what we had discussed in our previous class. So, here you find that we have two different components. One is clustering or forming compact clusters of the latent vectors coming from a category of images, and this can be attributed to the reconstruction loss or minimization of the reconstruction loss component. And the other part is all the distributions, they have to be very close to each other. And this is the part which can be attributed to the minimization of KL divergence loss component. So, now as every individual cluster is compact and the distributions of all different categories, they are also very close to each other. So, that simply means that if I simply take a vector, a latent vector at random from this latent space, then the decoder will be able to successfully decode or reconstruct the corresponding image. And because they are very close, all the distributions are very close, so it is in a continuous form. So, if I sample a vector from that latent space which was not used during the training process, but the decoder can give you a reconstruction which is basically interpolation of two different samples in individual distributions. So, when you go for variational autoencoder, the encoder part, unlike in case of traditional encoder, instead of giving a deterministic vector, latent vector, it gives you actually a distribution indicated by mean and variance of the distribution. We are assuming that these distributions are normal or Gaussian in nature. So, effectively what we want is, let us have a graphical model of this variational autoencoder. So, we have our input data which is x, and we have a latent vector which is generated out of x, which is z. Now, the generator part, what will do? It will do is, this z is sampled from the distribution in the latent space, and from this sampled z, the generator or the decoder is likely to generate my data. I expect that it will generate the data which is x. Now, as we have just said that in the latent space, we also want to maintain the class identity or the structural information of all the data. So, data for different categories will have different structural information and they will have different identities. So, as a result, we want to compute a posterior probability which is p z given x, because for x of different categories, the probability of getting a latent vector z will be different. So, we want to compute p z given x, and you find that p z given x is nothing but p of x given z into p of z upon p of x, and this is what you get from Bayes' tool. Now, over here you find that if I want to compute p of x, which comes in the denominator, p of x is simply given by p of x given z into pz into dz. You integrate this over z. Now, here comes the first problem or the first challenge that we face. The challenge is that this integral, that is integration of p of x given z pz dz, it is intractable. Why is it intractable? The reason being, when I consider this vector z, the z is a multi-dimensional vector. Its dimension may be 10, its dimension may be 15, dimension may be 100, and so on. And if it is so, then this integration, what we have shown over here, let me change the color, that integral p of x given z into pz dz, as z is multi-dimensional, so this integral also has to be taken over a multiple dimension. So, if the dimensionality of z, the latent vector z, is 100, then this integration will be over a 100 dimensional space, and which is very, very difficult. So, that is the reason we say that this integral is intractable. So, as this integral is intractable, then what is the way out? What we can do is, we can assume that there is a tractable distribution Q, and we want that this p of z given x has to be similar to p of z, q of z given x, where this q is a tractable distribution, fully tractable distribution, and we assume that this distribution will be a Gaussian and it will have a mean and a variance. And if I want to minimize, I mean, how I can make this p of z given x similar to q of z given x, I have to minimize the KL divergence between q and p, and by minimization of q and p, what I am effectively doing is, I am effectively playing with the parameters of the distribution p such that it becomes similar to q, where q is tractable, we know what it is distribution, right, and we are assuming that it is a Gaussian distribution with certain mean and certain variance. So, our objective now becomes that we have to minimize the KL divergence between q and p. So, now let us see what is this KL divergence. The KL divergence is defined as, between q and p is defined as sum of qx log of qx upon px, you take the summation over all x. That becomes the KL divergence between q and p. Before going further, let us try to discuss that how this KL divergence, or what is the genesis of this KL divergence. So, suppose we have a probability, two probabilities, one is Px, other one is Qx. So, when the probability distribution is Px, we know I can compute the information content. The information content is given by minus Px, then log of Px, take the summation over x. So, that gives you the information content when your probability density is P of x. Similarly, the information content when the probability density is q of x is qx log of qx, take the summation over x with a negative sign. So, now if I want to find out what is the difference or the divergence between these two probabilities, I can estimate that using what is the difference of information content of these two probabilities. Or in other words, what I want to find out, that minus px log of px minus qx log of qx summation of this. So, that becomes plus sum of qx log of qx. Now, in KL divergence, so what are these two components? This is nothing but the expectation value of log of px, where the expectation is taken with respect to p of x. This is the expectation value of log of qx, where the expectation value is taken with respect to q of x. Now, in KL divergence, this expectation of log of px is taken with respect to qx. So, if I take it with respect to qx, this simply becomes minus qx log px plus sum of qx log of qx. So, effectively this is nothing but sum of qx log of qx upon p of x, and this is what is the KL divergence, and that is what we have just said. So, let us come back to this, that the KL divergence between q and p is given by qx log of qx upon px, take the summation over x. And just an illustration that how can I compute the KL divergence given two different distributions. So, here we have taken two distributions. One distribution is p, which is a binomial distribution with p equal to 0 and n equal to 2, and the other distribution is an uniform distribution with p equal to 1 by 3. And this table on the right shows you this distribution in a tabular form. So, now let us see that how we can compute the KL divergence between these two distributions. So, given this, the KL divergence KL p given q is simply px log of px upon qx, which is, if you compute this over here, taking the values from this table that we have said, the value comes out to be 0.0414. Whereas, if I compute the KL divergence between q and p, so it was KL divergence pq, this is KL divergence qp, following this equation. Again, taking the values from this table, if you compute this, the value comes out to be 0.0375. So, this gives you one information, that KL divergence between PQ is not same as KL divergence between QP, or KL divergence is not symmetric. So, KL divergence PQ is not same as KL divergence QP. So, truly speaking, I cannot use it as a distance metric, because distance metric is usually symmetric. And the other thing is, the KL divergence is always greater than 0. So, though it is not symmetric, but KL divergence is always greater than 0. So, using KL divergence, I can estimate that what is the divergence or difference between two different distributions, and if I want to make those two distributions very close, then what I have to do is I have to minimize the KL divergence, and that is what is done in this particular case. So, what we have seen before is that we have seen that this p of x is intractable. So, if it is intractable, then there are two ways to deal with it. One of the option is you go for Monte Carlo simulation, and the other option is you go for variational inference technique. So, what we are going to discuss in this lecture is what is this variational inference technique. So, let us see what is this variational inference technique. So, you remember that our aim is that we want to minimize the KL divergence QP, okay, because P is intractable. We have assumed a tractable distribution QZ, and we want to minimize the KL divergence so that P becomes similar to Q, the distribution Q, which is tractable. So, effectively the scale divergence QZ given X and PZ given X, as we have just seen, that this is nothing but sum of QZ given X into log of QZ given X upon QZ given X. You can go further, it simply becomes log of QZ given X into log of Pxz, again coming from your base theory, upon Px into Qz given X. You take the summation over Z. So, that is the KL divergence between Q and P. If you expand it further, the same expression as you see over here, that my expression was Qz given X log of Pxz upon Px into Qzx. So, if I expand this, further simplify this, the expression becomes summation of, with a negative sign, Qz given X into log of Pxz upon Qzx, Z given X, minus log of Px. You go on simplifying, it becomes minus sum of Qz given X into log of Pxz upon Qz given X plus sum of Qz given X into log of Px summation over Z. Now, here you find that you are taking the expectation, the second component of this this expression, which is this one. This is nothing but expectation value of log Px with respect to Qz given X, and the summation is taken over Z, and Px is independent of Z. So, I can take Px out. So, effectively what I will have is this. If I take log of Px out of the summation, then sum of Qz given X over all Z, this is nothing but 1. So, the same expression is now simplified to minus sum of Qz given X into log of Pxz, that is the joint probability, upon Qz given X plus log of Px. I can rewrite this expression in this form. So, this is the expression that you have got. You can rewrite this as P of, or log of Px is equal to KL divergence between Q and P plus sum of Qz given X into log of Pxz upon Q of Z given X. You go on simplifying further. Here you find that since X is given, so the left hand side of log of P of X, log of P given X is fixed because X is known. So, but our aim is to minimize the KL divergence Q and P, KL divergence between Q and P. So, given this expression that log of Px is equal to KL divergence between QP plus sum of Qz given X into log of Xz upon Qzx, and here since the left hand side is constant, minimization of KL divergence amounts to maximization of sum of Qz given X into log of Pxz upon Qz given X. So, you find that we have come to a maximization problem. We started with a minimization problem of the KL divergence between two given distributions, and while simplifying, we have now seen that it is same as maximizing sum of Qz given X into log of Px given Z upon Qz given X. We will stop today's lecture here. In our next class, we are going to start from this point onwards. Thank you.